Okay, so we are going to evaluate the line integral. This is in, when you see the dx, even if there's no dy or dz, when you see the dx, you know it's in differential form. So we're going to evaluate the line integral over c of xy plus natural log of y dx, where c is the arc of the parabola x equals y squared from 1, 1 to 9, 3. So I like differential form because all you have to remember is put x and y in this case. If there's a z, it's true with z too. But in this case, there's only x and y. So put x and y in terms of a parameter t. But before you do that, you have to go ahead and parameterize the curve. So to parameterize the curve, x equals y squared, here's the trick. And I'll give you a general trick that always works. If your curve is defined by a function. So if the function, if it's y equals f of x, you're always going to let your parameter be the input. So if it's y in terms of x, y is a function of x, then you're going to let x equal t. So you're going to let x equal t. So x is equal to t, and then y is automatically f of t. Or alternatively, if you have x in terms of some function of y, then again, you just remember you let t equal the input. The input would be the y in this case. So if that's the case, then y equals t and x is equal to f of t. There's your parametric equations right there. And so if you can remember that, then you can come up with your parameterization, well, at least when the curve is defined as a function of x or as a function of y in a relatively straightforward way. So based on that, what do you guys tell me? What's t going to equal? So you have x equals y squared. So, okay, but what are you going to let equal t? So yeah, because it's x in terms of y, you think of it as x as a function of y. So you're going to let y be t, and then automatically x is equal to t squared. See how easy that is? It's a lot of math is just thinking about things in the right way. And then it becomes what seems hard becomes easier. Now, one other thing you need is the boundaries on t, right? So just think, if this is my first point, what would I have to plug in for t to generate x equals 1 and y equals 1? What would I have to generate for the lower bound on t to generate my first point? 1, right? Because if I plug in 1 for t, I get x equals 1 squared, x equals that 1 right there. And I get y equals 1, that 1 right there. And then my ending point, I have to come up with a t value that generates x equals 9 and y equals 3. What would that t value be? Well, you know y equals t, and you know y has to equal 3. So it's got to be, the upper bound on the t has to be 3 to get a y value of 3 at the end point. And then you just check. When I plug in 3, do I get 9 for x? Yeah, because I square it. I plug the 3 in right here. I square it. I get 9. So I know I have the right parameterization then. Okay? So it generates the correct beginning point. These parametric equations generate the correct beginning point and the correct end point. So then I just take this guy. Okay, I'm going to rewrite it. And if you really don't want to think very hard, just start plugging things in, okay? And you might have to find a differential at some point, but just start plugging it in. Okay, limits of integration. What does t go from? 1 to 3. Okay, x is equal to what? T squared. Y is equal to t. Multiply those together, you get t cubed. Plus natural log of y is t. Oh, we do need a differential here. dx. What's we didn't find that yet. What's dx? Yep. Just look at the parametric equation for x. Take the differential. dx is 2t, and then you need the dt on the end. So 2t dt. All right. Now we do get kind of a I don't know if it's a tough integral, but it's not as straightforward as some of them. Okay, do I have to distribute the 2? No, I'm going to put the 2 on the outside, right? But I do need to distribute the t. So what do I get if I distribute t? T to the 4th plus t ln t dt. And that's your setup anyway.